Hello, and welcome back to another IB Math Speedrun. So this is the first speedrun of the 4th day in the series, and today I will be covering chapter 1.4. So the first thing we need to cover, chapter 1.4 is all about counting principles and the binomial theorem. But before we start on the binomial theorem, we need to understand some parts about probability, namely permutations and combinations. So let's jump right in. So the first thing we need to understand is this little math symbol called the factorial. And the factorial, the symbol for it is an exclamation mark. So what is it? It's sort of like an operation to any other number. So it's like, you know, how we can raise numbers to powers, or we can divide numbers. Well, the factorial is sort of the same. So what the factorial does, if you put a number before it, is it means it's the product of all the numbers from 1 to this number. And okay, there's a more complex definition that we can get into later, but for now, just think about it as, say, 2 factorial is 2 times 1. Because it's all the numbers from this number to 1 multiplied together. So the value is 2. For like 4 factorial, this would be equal to 4 times 3 times 2 times 1, which is 24. So, yeah. I guess one of the most useful applications for the factorial is in probability. The factorial, if you take the factorial of a number, say 4 factorial, it's the number of ways you can arrange a bunch of distinct objects. This number of distinct objects. So what do I mean? Well, say we have 4 letters A, B. Actually, this will be quite long to write out, so let's make a text. Say we have 4 numbers A, B, C, and D. So A, B, C, and D, and we need to arrange them. How many ways are there of arranging A, B, C, and D? Well, we can go A, B, C, D, A, B, D, C, A, C, B, D, A, C, D, B, A, D, B, C, A, D, C, B, and then, so that's 6, and then we have B, A, C, D, A, D, C, B, C, A, D, B, C, D, A, B, D, B, D, A, C, B, D, C, A, and then we also have all of the other ones for C and D. It's pretty much the same. As you can see, there are 12 combinations here, and for C there will also be another 6, and for D there will be another 6. So C, A, B, D, C, A, D, B, C, B, A, D, C, B, D, A, C, D, A, B, C, D, B, A, and then D, A, B, C, D, A, C, B, D, B, B, A, C, D, B, C, A, and D, C, A, B, and D, C, B, A. And so if you count all of these combinations up, you'll get that there are 24 combinations in total. And what's special about the factorial is, since we have 4 terms, if we take 4 factorial, that's equal to 24. So it's the same thing for other numbers. And so that's one of the main ways we use the factorial. Now, we need to talk about combinations and permutations, which build onto the idea of, sorting things and factorials. So first, let's start with permutations. So as we just did there, the exercise we just did there, where we were just we were given 4 objects, and we were just sorting through all the combinations. That's actually a subsection of permutations. So what permutations tells us is the number of permutations of our objects out of a total of n distinct objects is n factorial divided by n minus r factorial. And what do I mean by distinct objects of N and R? Well, let's go back to our example where we had, let's go back to our example where we had letters A, B, C, and D, and that's all good. And we know that it's 24 if we sort it. But what if we could only pick 3 out of the 4 letters? How many permutations would we have then? Well, let's count them up. ABC, ABD, ACD, ACB, ACD, ADB, ADC, BAB, yeah, so actually, wait, this would give the same amount. This is a pretty bad example. No, it's fine, actually, honestly. BAC, BAD, BCA, BCD, and then BDA, BDC. And if you count them all up, you'll realize that we get 24 again. So even though we're picking one less object, it doesn't matter, we get the same amount. And we can actually calculate the number of permutations, or the number of different ways we can arrange it using this formula. So N is the total number of objects, in this case it's 4, and R is the number of objects we're picking out of them, which is 3. So the total number of permutations would be 4 factorial divided by 4 minus 3 factorial, which is 4 factorial over 1 factorial. And this is equal to 4 times 3 times 2 times 1 over 1, which is also equal to 24. So let's try it for something that would give a different result. So say instead of all of these 4 numbers, the 4 letters, we can only pick 2 of them. Well then, what are our possible combinations? We have AB, AC, AD, BA, BC, BD, CA, CB, CD, and DA, DB, and DC. So that is 12 combinations in total, and what would our formula give us? So we have the number of objects, which is 4 factorial, divided by the number of objects, again, minus the number we're picking out of them, factorial. So this would be 4 factorial, 4 times 3, times 2, times 1, divided by 4 minus 2, which is 2 factorial, which is 2 times 1. So if we cancel out the bottom and the top, we're left with 4 times 3, which is 12, which is exactly the number of permutations that we have. Okay, so now that's clear, we'll move on to the final thing we need to talk about before we start on some questions, which is combinations. And so, going back to our 4 letters, A, B, C, and D, let's say we also want to pick 3 letters this time out of the 4, but we don't care about the order of the letters. So, in this case, ABC and BCA are the exact same number of, are the exact same pair. So we would only count, this as a duplicate, and so we would only count ABC. Well, how many different ways are there for us to pick out of these 4 letters 3 letters? So there would be ABC, ABD, ACD, BCD. That's it. So if you went through the 24 different combinations of that we picked out earlier, where the order did matter, as you can see, they all fall into one of these 4 subcategories, and it's just a rearrangement of these 3 letters. And so how do we calculate the combinations? So the combinations is equal to the number of objects divided by the number of objects we're picking times the number of objects minus the number of objects we're picking, factorial. So one thing I didn't mention is that normally we write this as NCR and NPR. So, for example, this would be n factorial over n minus r factorial. And so if we, in this case, we have 4 objects and we're picking 3 distinct ones out of them. So for NCR, this would be 4C3. We replace the n and r's with the numbers we're getting. And so this would be equal to 4 factorial divided by 3 factorial times 3 minus 1 factorial. Sorry, 4 minus 3 factorial. And of course, this is equal to 4 times 3 times 2 times 1 divided by 3 times 2 times 1 and then times 4 minus 3 factorial, which is just 1. So as you can see from here, we can cross out these and we're simply left with 4 as the result. And that is how many combinations we got in the end. Okay, so now that all of that's clear, I think we can jump into some problems regarding factorials. So as always, we will be doing every odd, well actually today I'm feeling even, so we'll do every even problem. So first problem is to find the value of, and the first question is 8 factorial divided by 4 factorial times 6 factorial. And so the most handy way to do these factorials is not actually to calculate what 8 factorial is and then divide it by 4 factorial, but is to write it out as like its whole expression. So 8 factorial is equal to 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and we divide all of that by 4 factorial times 6 factorial. 4 factorial is 4 times 3 times 2 times 1, and 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. So instantly we can cross out this section, and we're left with 8 times 7 over 4 times 3 times 2 times 1. We know that 4 times 2 is equal to 8, so we're left with 7 over 3 times 1, otherwise known as 7 over 3. So that is our answer. Okay, let's move on to the next question. And we have find the value of, skip to C, 10 factorial times 8 factorial divided by 11 factorial times 6 factorial. I'll teach you another trick with these. So we know we have 10 factorial at the top, and we also know that 11 factorial is equal to 11 times 10 factorial, since 10 factorial is 10 times 9 times 8 until 1, and to get 11 factorial from 10, we just multiply by 11. So we can write in this kind of form. Split it up into 11 times 10 factorial, and this will make our life easier later. Similarly, on top, we can write 8 factorial as 8 times 7 times 6 factorial, so that we can easily remove the 6 factorial on the bottom. So as you can see here, we have something much simpler than writing out all the numbers. We can straight away cross out the 10 factorials and the 6 factorials, and we're left with 8 times 7 divided by 11, which is 56 over 11. And that would be our final answer. Okay, let's move on to the next problem. So the next problem is show that, it's a long one. So let's see what it is. Show that 2n plus 2 factorial times n factorial squared over n plus 1 factorial to the minus 2, squared, n plus 1 factorial squared. I don't know why I have an extra line there. Times 2n factorial. Sorry, 2n factorial on the outside. And we need to show that this is always equal to, which we use the identity sign for, and I'll talk a bit about the identity after, but 2 times 2n plus 1 divided by n plus 1. So what the identity sign means is that this is true for all values of n, regardless of what n actually is. So it's not like an equation where we have to prove that we have to find a certain value of n that satisfies both sides, but we actually need to prove, in this case, that it is true for all values of n, and it's similar to a proof. We have to prove that this side is equal to this side. So, how are we going to do that? Okay. So, about this. So, first of all, let's simplify 2n plus 2 factorial as 2n plus 2 times 2n plus 1 times 2n factorial. And we can do that because 2n plus 2 factorial is equal to this, because it's like 2n plus 2 times 2n plus 1 times 2n factorial, which is the product of all the numbers from 2n to 1. And then we have n factorial squared, which we can actually leave as n factorial squared for now. And what we're going to do is we're going to do something similar for this n plus 1 factorial squared at the bottom. So if you realize n plus 1 factorial squared is equal to n plus 1 times n factorial all squared. And we can simplify this into n plus 1 squared times n factorial squared, because they're being multiplied together. So if we square both of the components inside, the value does not change. So we can do that. And we need to multiply it by 2n factorial. So something you notice here is, first of all, we can straight away cancel out the 2n plus 1 factorials on the top and the bottom. And we can also cancel out the n factorial squared on the top and the bottom, leaving us with 2n plus 2, oh, it's in red, 2n plus 2 times 2n plus 1 divided by n plus 1 squared. And the other thing you need to notice is that 2n plus 2 is actually equal to 2 times n plus 1. So we can bring the 2 outside the brackets and put n plus 1 inside. Finally, we can cancel out this n plus 1 and remove the square here. So we're left with the fraction 2 times 2n plus 1 divided by n plus 1, which is, I think, what we need to prove it equals. Let's just check. 2 times 2n plus 1 divided by n plus 1. Yep, that's exactly what we needed to prove. So we've solved that problem. Okay, let's move on to the next one. Not that. Here. Okay. So we need to solve the equation. Okay. Solve the equation, and I'll write it out. 16 times n minus 1 factorial is equal to 5n factorial plus n plus 1 factorial. Okay, where n, of course, is an integer. So how do we do this? Well, we know that 16n minus 1 factorial is equals to 16 over n times n factorial. and of course is equal to 5n factorial, and we know n plus 1 factorial is equal to n plus 1 times n factorial. From here, we can divide both sides by n factorial, so simply cancel those out, and we get 16 over n is equal to 5 plus n plus 1. And this turns back into a pretty simple quadratic equation. So we have 16 is equal to 6n plus n squared by multiplying both sides by n. So n squared plus 6n minus 16 is equal to 0. And now we can simply factor this into n minus 2 times n plus 8 is equal to 0. Oh, and sorry, it has to be a positive integer. I have read this slightly wrong, so it has to be a positive integer. No, when we write z plus, I butchered it. No, when we write z plus, this means that n is a positive integer. So from these results, the only positive integer case of n is when n is equal to 2, or when n minus 2 is equal to 0, therefore n equals 2. So that is our final answer, that n equals 2. Okay, let's move on to the next one. So we have 8 safe with 2 digits, 2 dials. One with 26 letters and one with the digits 0 to 9. In order to open the safe, Rose has to choose a code consisting of 3 distinct letters followed by 2 distinct digits. Determine how many safe codes are possible. So this looks like a classic probability scenario where we're using permutations. So to get how many possible ways there are choosing 3 distinct letters, we have to use permutations. So we would go 26 permutations, and since we're choosing 3, we can just put 3. And so I don't think order should matter. I think order should matter because it should matter, what order you put the letters in. So that's why we're using permutations and not combinations. And then afterwards, we'll multiply this by the number of permutations for the 2 distinct digits. And so since there are 10 possible digits, 0 to 9, and you need to pick 2, this is 10 times 2 permutation. So what is this? This is 26 times 25. I mean, okay, the I guess cheaty way to do it is that 26 permutation 3 is equal to 26 factorial over 26 minus 3 factorial, which is equal to 26 factorial over 23 factorial. And you know that 26 factorial is 26 times 25 times 24 times 23 factorial divided by 23 factorial. Simply cancel these out and you're left with 26 times 25 times 24. So the actual shortcut to do it is whenever you're doing permutations, if it's like a smallish number that you can realistically do, 26 permutation 3 is simply get the 3 largest integers that are equal to or less than 26, and yeah, that's pretty much it. So you just count backwards from 26 to 1 the number of objects you need to pick. So in this case, 26 permute 3 would be 26, 25, 24. So this would be 26 times 25 times 24, and we can use the same trick for 10p2, and we just count backwards from 10 the number of distinct things we need to pick, and that's just 10 times 9, since there's only 2. So 26 times 24, 25 times 24, times 10 times 9, and that would be equal to 26 times 25 times 24 times 10 times 9. You should get 1,404,000 ways or combinations, and it's a pretty secure safe, as you can see. I don't think any robber would ever have the time to try 1 million combinations. So yeah, that's it, and let's move on to the next one. Our final question, is it? No, it's not. So we have quite a long question, actually. We need to do how many 4-digit numbers can be made using the digits 0, 1, 3, 4, 5, 8, and 9. Okay, so you might think to yourself, oh, this is pretty easy. It's just, how many terms are there? 1, 2, 3, 4, 5, 6, 7. So it's just 7 P4, since we have to pick 4 digits out of the 7. And this is the first step, but you're still missing a part. So 7P4 is equal to 7 times 6 times 5 times 4. And the only thing is, we can't have 0 at the start of the 4-digit number. Like 0, 1, 3, 4 is not a 4-digit number. That's just 134, and that's a 3-digit number. So we need to find a way to eliminate all of the results that hand us a 0 at the start. And there's a pretty simple way to do that. It's we simply have to divide 7P4 divided by 7. So actually no, technically it would be 7P4 over 7P it would be 7P4 divided by let's think, 6P3, and all. So the reason why we're dividing it by 6P3 is we need to count the number of cases that, say we have picked 0 as the first number, we need to count the number of numbers that could be created from these 3 digits, and actually just subtract it, not divide. So how many ways are there of picking 3 distinct digits that go after this 0? And the answer is, well, we're choosing from 1, 2, 3, 4, 5, 6 remaining numbers, so it would be 6, P, and there are 3 digits to pick from, so it's 3. So we have to subtract from the number of permutations of picking 4 numbers from 7, we need to subtract the number of permutations in the case that the first number is 0, and there are this many permutations. So after we do 7P4 minus 6P3, we get 7 times 6 times 5 times 4 minus 6 times 5 times 4. And so this is simply equal to 6 times 6 times 5 times 4, which is equal to, what is this, 36 times 20 is like 100, and it should be like, I think 1,800. I think it is asking, I think the digits don't have to be distinct, which changes a lot. So what I mean is that I'm reading the mark scheme and it's giving me a different answer. And the thing is, I think they're accepting like 8888 as like a valid 4-digit number, which it is a valid 4-digit number, but I didn't know that the digits don't have to be distinct, which changes our calculations a little. So we still need to account for the fact that 0 cannot be the first number. And so how many numbers can be in the position of the first digit? There would be 6 numbers. How many can be in the position of the second digit? 7. Third digit, 7, and fourth digit, 7. And so the sum is pretty simple. It's just 6 times 7 times 7 times 7, which is equal to 6 times 7 times 7 times 7. It's equal to 2058, which is the correct answer. Okay, so let's try maybe a harder one. This is actually a multi-step question. So now we have to answer how many of the 4-digit numbers have no repeated digits. Well, we solved this one earlier. If you remember, it's 6 times 6 times 5 times 4, which is equal to 720, and that is correct indeed. So now our next question is how many 4-digit even numbers can be made using the digits? Okay, so I think they don't have to be distinct again. So how many even numbers do we have? We have 4 and 8. So for the first number, we have 6 options for it. For the second number, we have 7 again. For the third number, we have 7. And for the last number, we actually have 3, 0, 4, and 8. So we have 3, because the last number has to be either 0, 4, and 8 for it to be an even number. So getting 6 times 7 times 7 times 3 gives us the answer. So that would be 882. And so that would be our answer. And let's move on to the final question, which is how many of these even numbers are divisible by 5? And the thing is, of the even numbers, the only even number divisible by 5 has to end in a 0. So this is pretty simple. How many numbers can be in the first number? 6. How many numbers can be the second number? 7. Any of the numbers. Remember, you can't have 0 as the first number. That's why it's 6. How many can be the third? 7. And how many can be the fourth digit? Well, it can only be 0, so it's just 1. So our answer is simply 6 times 7 times 7, which is 42 times 7, which is 294. So that is our final answer. Now let's move on to the final question. And let me just plug in my laptop before. Okay. So the final question will be, where is it? A group of 12 people want to go to a concert. They can travel in a small car that takes 1 driver and 1 passenger, and 2 cars each taking 1 driver and 4 passengers. If there are 5 drivers in the group, in how many different ways can they travel? So this is going to be combinations, obviously, but let's see where this goes. First, you have to pick the driver of the car. Out of the 5 drivers, there are only going to be 3 drivers, since there are only 3 cars. So to pick the driver, we have to, and order does order does matter in this case for the simple reason that, okay, it actually matters which car they're driving, since that would be a different way of traveling. Even if you have the same 3 drivers, if they're driving different cars, then that would be a different method of travel. So we would have 5 choose 3. 5 P3. Since we're picking 3 from 5, and we need to multiply that with the remaining people. So we have to sort the remaining people into, well, there's 1 person, there's 4 people, and there's 4 people. How are we going to do that? Well, this would be the simplest way. So you have 1. So you need to first get 4 people to go into the second car. And the order doesn't matter, since, if the same 4 people are in the car, even if they, are sitting in different seats, they're still traveling through the same way. So in this case, it would be, how many people do we have left? 9 people, choose 4. And then we would need to multiply this with the remaining, we would choose another 4 people for this car. So we would have out of the remaining 5 people, we need to choose 4 of them to ride in that car, leaving us with 1 person to ride in the small car. We don't have to do 1 choose 1, since that's just 1, and yeah. So if we calculate this, we should have the number of different ways they travel. 5 permute 3 is 5 factorial. Let's put this all into 1 fraction. So 5 factorial divided by 5 minus 3 factorial, which is 2 factorial. And 9 choose 4 is equal to 9 factorial divided by 4 factorial. 4 factorial, let's put this closer. 9 factorial divided by 4 factorial times 9 minus 4 factorial, which is 5 factorial. And then we have 5 factorial here times 4 factorial times 5 minus 4 factorial, which is 1 factorial, which is just 1, so we don't need to include it. Okay, straight away we can cancel out these 2 5 factorials, and we know that we can write 5 factorial as 5 times 4 factorial. So we can cancel out another 4 factorial. Next, we can write 9 factorial as 9 times 8 times 7 times, that's 5, times 7 times 6 times 5 times 4 factorial. And so we can cancel out this 4 factorial as well. So what we're left with is 9 times 8 times 7 times 6 times 5 times 5 divided by 2 factorial, which is just 2 times 1, but 1 is kind of irrelevant here. So we can simply divide, say, 8 by 2, leaving us with 4, and so we have the remaining 9 times 4 times 7 times 6 times 5 times 5. 9 times 4 times 7 times 6 times 5 times 5 is equal to 37,800. Is that the correct answer? No. Very interesting. So, where have we gone wrong? I think this needs to be a combination, and that's why we're wrong. Which is, I guess, a bit odd. Would it be a bit odd? Yeah, it would be a bit odd for me, but it's the answer they are looking for. So we need to add a 3 factorial down here, which adds a 3 times 2 down here. And so our answer would be equal to 6,300. And that is the answer they're looking for. I mean, have I made a mistake? Why would it be 5 choose 3 for the drivers when they're all driving different cars and you need to account for that? I'm not too sure. I guess it's because the driver is technically a passenger. So that would be the reason why. But anyways, That's it for this first speedrun of the day. I hope you liked the speedrun, and if you did, if you want to learn some more math, follow along with my next speedruns. If you have any comments, leave them down below, and I hope to see you in the next one. Ta-ta!